Yeah, hi. I'm Philippe Proulx. I work for EfficiOS with Mathieu and Jérémy, who's going to follow. We're based in Montreal, Canada. I have a strong interest in file format in general, tracing, of course, and documentation. I happen to be the author of this revision of the common trace format. We'll go into the details of what CTF is if you don't know this. So this is the contents. So I don't expect everyone to know what CTF is. So I'm going to first show you what version 1 is, what the current CTF ecosystem is, so who produces or what produces CTF and what consumes CTF. What are the limitations of the current revision of CTF and how we solve those limitations with CTF2? And what is the planned adoption by tooling for both producers and consumers of the trace format? I'll do the Q&A at the end of the presentation, but you can also interrupt me if you have urgent questions. So what is CTF exactly? The acronym stands for Common Trace Format. It is a self-described binary trace format. The first revision was specified in 2010 or 2011. Its main focus was on the producer's performance. So some examples of features which allow this are that it supports big indent and little indent fields, so that the producer can write its native field as is in the binary stream. It doesn't need to be a per trace configuration, so some fields can be little indent, some other big indent. It supports bit fields, so integers or bit arrays with custom size in bits. You can have 27 bits, for example. Integer, little indent integer followed by 5-bit integer before a 32-bit word. It supports custom field alignments, so that the tracer does not need to do spatial alignment while tracing. And it supports multiple data streams. So usually a tracer will output one stream per stream. To avoid any form of packet concatenation of different streams. So what's inside a CTF trace? It's made of one or more data streams, which are pure binary streams outputted by the tracer or by the producer. Those data streams contain packets, so they are sequences of packets. And within each packet, you have multiple event records, the actual events that are recorded by the tracer. There's no description of the layout of the data streams within the data streams. A separate metadata stream does or provides this description. In CTF1, the metadata stream contains a textual representation of the data stream layout written in TSDL, the trace stream description language. And as I will show you, we move to JSON for CTF2. So give you a short example. At the left, in green, you have the metadata stream. So this is the description of data streams which are described by it. So we can see all the colors associate what is described in the binary data stream at the right. So for example, we start with a 64-bit little indent timestamp in red. That is followed by a 16-bit big indent ID. And we can see in the data stream here that it's 17 in X, so 23. So we select the event which has the ID 23. happens to be an event named new message, for example, which starts with a 32-bit little endian, and let's pretend it's aligned on 32-bit too. So we skip 2 bytes of padding in gray, and 2 bytes which are 0 here. And we get some message ID followed by a C string or an terminated string, after which would start the next image report or another packet perhaps. So the benefit of having a common trace format is that you can use common tools to read a trace, a CTF trace, and common tools to produce it also. There are a few elements in this slide, but of interest maybe is that LTTNG produces CTF traces natively, as you can see at the top. Perf has a tool which can convert its own format to the CTF format through the CTF writer lib. CTF writer lib is provided by the Babel Trace project. So if you build Perf with the specific option to include data convert to CTF, and that you have Babel Trace, you can go from the Perf trace to the CTF trace, and then once you have a CTF trace, you can use UI tools like Trace Compass and Babel Trace to read it and analyze it. So I'll go through a few limitations, or the most important limitations of CTF1 and how we solve them with the design of CTF2. So one of the main problems with the metadata language of CTF1 is that it's somewhat hard to consume. When I say hard to consume, I mean hard to develop a very compliant parser for the metadata language. Its grammar is somewhat complex. It's a declarative subset of the C language with some additions specific to the tracing domain. It has many implicit parsing rules, so that's more code to put in the parser than only to remove some text in the metadata. For example, it has a bunch of magic field names, so you need to know some specific field names at specific locations, which have specific semantics. So, for example, in a trace packet header, if you have a UUID field, it means that it's the trace's UUID, which you can compare with the metadata provided UUID. Also, event ID, event timestamp. Those are all provided by field names. It supports currently type aliases, but they are lexically scoped, so some type alias can shadow another one, and you have to keep a stack of type aliases and their current mapping. So that's more complexity in the parser also. So all that is really useful when you write the metadata stream manually with a text editor, for example, and then you have your producer actually produce the content. But I wrote who does that because over the years we noticed that nobody does that. So usually the tracers generate the metadata stream, so the tool generates it anyway. So we don't need such a complex grammar just to help the manual users. So drink some water while we try to understand this grammar. And that's just a basic example, but there are really more grammar rules in there. So attacking this problem can be frustrating. So our solution is to move to JSON for the basic grammar. JSON is super simple. There are tons of libraries and the different programming languages to ease your life with that. Also, we plan to require more explicit references and descriptions. So all those magic fields, for example, that I mentioned earlier. They can be directly tagged within the metadata instead of relying on special field names. We plan to keep the type alias feature. So a type alias is associating a name to a field type. For example, the name, it's like a type difference. But in this case, we will keep only one level, so only one mapping of name to types. And one very important thing is to keep remain semantically compatible with TSDL, which is CTF1's metadata language, because we want to be able to convert from a CTF1 trace to a CTF2 trace by only translating the metadata without touching the data streams. So it remains, CTF2 remains completely binary compatible or data stream compatible with CTF1. So the conversion should be fairly quick. So that's a small example of going from TSDL to our JSON representation. Again, the colors are used to match at the left and right. So it's a bit more verbose, but again, we don't write it manually, so who cares? I mean, the tracer doesn't care. Yeah, another limitation is that the TSDL language has a very strict grammar, which makes it hard to extend. So there are no really extension points that are specified by CTF1. And so there are things now that we want to do that maybe we didn't think about a few years ago, well, when CTF1 was designed, that we cannot express now unless we do some hacks, but then the readers, they don't know those hacks, so that their parser can fail. For example, having format strings attached to get specific types or maybe specific event record classes. ftrace does that. It has a format string for each event description. So we could have this feature too, but there's no place to put it right now in the metadata language. We also want to be able to tag specific fields as being instruction pointers, so as being addresses of instruction pointers. I'll show you an example on the next slide. Or another example, tag a specific field as being a stack trace. So right now we could have, say, an array or a sequence of string fields, maybe or a sequence of structure which contains strings and integers, and this would represent a stack trace, but the reader has no way to know it, so it has no way to show this specific field as a stack trace. Pretty primitive, for example. So right now we have to rely on field names, but this is precarious, as I'll show you. For example, this is a part of what LTTNG outputs today. So when you add the IP context field to some LTTNG channel, and you get this magic IP field, which means instruction pointer, and Babel trace knows this IP field as being the instruction pointer when the trace is identified as being an LTTNG trace, and then it can add debug info to the output, for example, using this IP field, but it's just a simple field. So it could mean for another tracer an IPv4 address on 32-bit, for example. So our solution is to add a user attributes property in selected metadata objects, so field types, event classes, and so on. I'll show you an example on the next slide. So user attributes you can use any JSON in those user attributes as long as you namespace your attributes or custom attributes to your specific tracer, vendor, or the specification itself, so that there are no conflicts in the future. Here's an example. This is similar to the previous slide where I had this IP field. Now my field is not named IP anymore. It's named font add, but it still represents an instruction pointer address. So right now, Babel trace will have no way to know that this is an instruction pointer, but we can add a specific user attribute. I namespaced it, for example, under the LPTMG tracer, but later it could become a specification namespace. And I just put his IP through so as to mark, so as to tag this field as being an IP. So this is going to be the interesting feature. And finally, CTF1 is currently missing a few useful field types, which would make our lives easier. One of them being that all the integer field types and the inversion field types have a fixed number of bits for their size. But in some scenarios, the values of the fields represented by those field types are almost always small and sometimes big. So a useful field type in this scenario is to have a varlen integer or varlen enumeration. So we plan to support this and to use LED 12.8, which is the encoding of UR and it's very popular. Also, CTF1 cannot express Boolean fields. We currently use integer fields for this, so when the field is 0, it means false. But in programming languages, bools and integers have different meanings. And so, yeah, it's interesting to represent false and true without caring about the actual integer value of traces. Again, CTF1 has a way to express fields which have no length. This can seem like it's useless, but it's not actually. We sometimes use empty structure fields for this. So structure field that contain nothing. One of the use cases is to represent a variant choice which is nothing. So, for example, an optional field would be a variant, so a discriminated union, where the choices are null and, well, the actual field that's optional. Could also be used to align the consumer without actually consuming any payload data. So again, we use an empty structure field which has an alignment, specific alignment for this use case right now, but it's kind of a factor. Finally, CTF1 has a variant field type, which is a discriminated union, but it doesn't have any union like in C, where you describe the same payload bits with different layouts. So this can be interesting to provide alternative views of the same binary data. And also we plan to use this union field type to introduce new field types in revisions of CTF2. So we want a consumer which only knows the initial revision of CTF2, for example, to be able to consume all CTF2 traces. So if we put new types in unions, then we can provide a known alternative to all consumers. So I have two examples. For example, having an IP address. An IP address can be represented on a 32-bit big-endian integer and can be split in 4 like we usually see it in a 4-byte array. We could also tag an IP address with a is IP address user attribute, for example. And also, if we say that we introduce a UTF-16 string in the future, we could wrap this string with as being a sequence of bytes, so that a reader which doesn't know the UTF-16 field type can decode it as a simple sequence of bytes. You don't get the string, but at least you can continue decoding the data string. So about the planned adoption for Babel trace, Jeremy will follow with a presentation about bubble trace if you don't know this tool. We're about to release 2.0 bubble trace, but CTF2 support will only come in 2.1. For LTTNG, we're at 2 currently, so maybe 2.11. Well, probably not 2.11, 2.12 maybe. Yeah, the CTF and scope will follow the other projects to adopt CTF. It also depends on how active is the discussion. So I have resources here where I posted a proposal for a specification and the other documents which accompany this proposal. So if you have a word about that, you can reply to this very old thread, and I'll be glad with you. So that's about it. Any questions?
So for the questions, please use the microphone because we are recording this event. So thank you. Students?
Sure. I'm just curious about the format for CTF for reading a packet that has like condition, like dependent, for example, for trace command. With one of the, not just a packet, but a record within the packet where you have a field that determines what type, how to read it. Say it's basically in a single field that from its, I think we have, how many bytes it is, 28 bits, a 28-bit field where the first up to like the number 30, where actually it's 5 bits because it's up to 32. So from 0 to 27, that's the size. But if it turns to 28, it actually changes the type of the actual packet.
The size of what?
The size of the data that's attached to the, I shouldn't say packet, record. What's within the packet? Event. So the size of the event. So each event has a header that determines what type of event it is. So you have one of them, but that same field could either be the length of the data attached to the payload for the event, or if it hits a number, it changes the actual event type. I'm just curious. You did very simple examples. I was wondering how you handle in format, how do you handle like say if statements?
Yeah, I know you're talking about the header of F-trace events, right?
Yes. Yes.
Well, the variant or discriminated union in CTF is kind of very powerful. So you can select something using an enumeration, which is an integer, and integer field types can have any size in bits. So you could use a partial bit field as the tag, and then choose whatever you want depending on that.
So I guess my question, I guess it's simplify the question. So it's not, how difficult is it to take one part of a event and use it to determine how to read the other parts of the event? I think that's pretty simple, straightforward.
Yeah, I mean, what Philippe said, I mean, the variant type really allows you to say, okay, this enumeration entry is a range from 0 to 30, let's say, of the value, of the 5-bit value. And that means what follows is going to be that layout, which uses it as a size. Or if it's, let's say, 3031, then it's a different layout.
Okay.
And so the variant allows to do exactly that.
Yeah, I figured it did. I was hoping to see an example. That's why, but that's okay.
Oh yeah. Well, I didn't go into like details in this presentation because I had 15 minutes originally.
Right, I understand. No, I was just.
But maybe also it could be that you, instead of different event layouts, you select different event classes. So your actual 5 bits or something selected event ID. That's another possibility that FTNG does, but yeah, variants really usually solve this kind of problem.
Okay, thank you.
Other questions?
You can come talk to me later if you have
All right.
questions afterwards.
So Jeremy?